All right, senior math, welcome back. Today we are continuing to talk about normal distribution. We are going to jump into something today called z-score, which is why we were using all these z's last time in normal distribution. So z-score is a fancy way of us using normal distribution to be able to determine the probability of different real events. So we're going to start off with this warm-up that you had. Calculate the following probabilities using the normal distribution chart. So probability that p is less than 2.54. So remember, in order for us to do this, we need that normal distribution chart. So we are going to look for that number 2.54 on it. So we're going to flip over to our positive side. We're going to go down to 2.5. And then this is 0, 1, 2, 3, 4. So 0.99446 is going to be our probability. So whenever we're less than, all we have to do is just take that number, which was 0.99446. And that was our probability. Now, if we were greater than, for example, if z is greater than 2.54, then whenever we were greater than, we were looking for the above value because this was a cumulative chart. So it worked a little bit differently. So we had to do 1 minus 0.99446. There was never going to be an equals, remember, because there was a continuous number, an infinite number of probabilities. So whenever we were less than, we just took the number. Whenever we were greater than, we had to do 1 minus, which is 1 minus 0.99446, which turns out to be 0.00554. And then if we had an in-between, for example, if the probability of z being greater than negative 2.54 but less than positive 2.54, we took the bigger number, 2.54, which we know is 0.99446, and then we subtracted the smaller value, so we're going to have to look up the negative 2.54 on our table. So negative 2.5, 0, 1, 2, 3, 4 is going to be 0.00554. And we notice both of those should always add up to equal, it's this number right here, because both those numbers should always add up to equal 1, the positive and negative versions of themselves, with how the table works. So we're going to do 0.99446. And we are going to subtract 0.00554. And we're going to end up with 0.98892 is our value. And so those should be our answers we got from our warm-up. So that was our normal distribution chart that we were using last week. Now we are going to continue using this, and we're going to add something on to it called z-score today. That is going to be our goal for this activity today. All right, so moving on. So this week we will continue to learn about normal distribution and continuous variables, but in order to talk about normal distribution, we need to review some things from earlier this year. So this little symbol right here, this U with a little tail on it, this was the symbol mu. It's the Greek letter mu, but it stood for the mean of a data set. So the mean, the average. Remember, the mean is when you add up all the numbers. When you add up all the numbers of a data set and divide by however many numbers there are, that gives you the average result. That is your mean. So anytime when you see that mu symbol, that U with a tail, that means the mean of the data set, the average of the data set. This little O with a little line coming off of the top of it, like a little flat bill, this is sigma, the Greek letter sigma. But this Greek letter represents standard deviation. Now, standard deviation was important because standard deviation taught us or told us how far away on average were each of those points from that mean. What is that average deviation of that data set? And so we said we were going to use mean and standard deviation. We said we were going to bring these back earlier in the year. Now we're going to bring them back. So in order for us to be able to use z-score, what we're going to talk about today, we need to know the mean of a data set and the standard deviation of a data set. Luckily, we learned how to calculate both of those earlier this year using that Desmos calculator. We can plug all the information into the Desmos calculator. We can find the mean. We can plug it into the Desmos calculator and find the data set or the standard deviation. So luckily we can find those both easily with that. All right. The normal distribution chart is also known as z-score table. So by finding the z-score of the data point, we can determine the probability of the result occurring. So that score, that number we are always looking up, that is the z-score. So by finding that, you can look up the probability of that number occurring. So the z-score represents how many standard deviations away from the mean a data point is, meaning the more standard deviations away, the less likely is that point to occur. So the z-score represents whether it's a number is how many standard deviations above the mean it is or how many standard deviations below the mean it is. So the more standard deviations away from the mean, the less likely it is to occur because it's farther away from that average. It's less likely to happen. While if it's closer to 0, that means it's closer to the mean, closer to the average, meaning more likely to occur. So that z-score probability determines how likely it is. So let's do an example of calculating z-score. So on a 35-point test in a biology class, the mean test score was 25 and the standard deviation was 4. What is the z-score for a test score of 30? So this z-score formula, this is the z-score formula we're going to use. Sorry, I didn't talk about it on the last page. I'm sorry. This is the z-score formula we're going to use. So your z-score, the number we're always going to look up from the chart, is going to be your answer. So this z-score part, this is going to be your answer. This is always going to be equal to a data point. So we're always going to be given a data point or a certain value minus the mean, so minus the average, and then divided by the standard deviation. We always want to subtract the mean first. So we subtract the mean first, then we divide by the standard deviation. So it's really just two operations. Take your number, subtract the mean, divide by the standard deviation. So for this question, we're asked, what is the z-score for a test score of 30? So x in our problem is going to be 30. That's the value we're looking for a test score of 30. We were also told that the mean test score was 25. So the mean is 25 from our data, and that the standard deviation of the test was 40. Or was 4, I'm sorry. So we have an x of 30, a mean of 25, and a standard deviation of 4. So our z-score is going to be equal to 30 minus 25 divided by 4. So whenever we calculate these, we always need to subtract the top part first and then divide. So 30 minus 25 is going to be 5. 5 divided by 4 is going to give me 1.25. And that would be my z-score that I would look up. So then we would go to our table, look up 1.25, and that would be our result that we need. Now, obviously, we also need to determine whether we're going to be greater than, less than, in between two numbers, and so that will come up later. But this is just how we calculate using this little formula, this z-score formula. Take your value, minus the mean, divide by the standard deviation, and you're good. I don't want that up there. Sorry. All right. So by combining the z-score with our normal distribution chart to find the probability, the z-score can be a valuable tool for determining whether a particular observation is likely to occur quite frequently or whether it's unlikely to occur or might be considered an outlier. So we can use that z-score table to determine probabilities on how likely things are to occur. But it also can be helpful with determining whether something is an outlier or not. So remember, an outlier is a point that is much larger or much smaller than the rest of the data set. So if we think there's a point that is an outlier, we can test it. We can look at the z-score of it, and if that z-score is like bigger than 3 or less than -3, if it's in far away from 0, then that's going to help us determine that it's an outlier. So like consider this data set. So we have 1, 1, 0, 15, 2, 3, 4, 1, or 0, 1, 3. So of this data set, what number appears to be an outlier? Well, all these numbers are really small except for 15. So 15 appears to be a data set, or appears to be an outlier. So we can use the Desmos calculator. By plugging that information into the Desmos calculator, we can figure out that the mean is 3 of this data set, and that the standard deviation is 4.422, or 4.42. What is the probability of receiving a result of 15 or greater? So we're looking for the probability that our number is going to be greater than 15 or greater. Now, it doesn't necessarily matter whether I have greater than 15 or greater than or equal to 15, because we said the equals don't matter because there's so many possible numbers that we could be using for these that the value of just being equal to one specific number doesn't matter. So probability of x being greater than or equal to 15. The first thing we have to do whenever we're solving one of these problems is we need to change this to a z-score. So rather than having it as an x, I want the probability of z being greater than the z-score. So I need to figure out what is the z-score that needs to go right here to solve this. Well, luckily, we just figured out how to calculate the z-score. So I can do z is equal to my x value minus my mean divided by my standard deviation, which I can plug in that information. So my x value was 15. That's the value I'm using. I'm looking for a result greater than 15. My mean was 3, and my standard deviation was 4.42. So I can calculate this. So I can do 15 minus 3 divided by 4.42. So 15 minus 3 gives me 12 divided by 4.42 gives me 2.71. So we're going to look for the probability that z is greater than 2.71. Now we know 2.71. We know we can calculate that from our z-score table. But remember, if z is greater than 2.71, I need to do 1 minus that z-score. And now I'm going to look up 2.71 on my table. So 2.71, I need to go to the positives down by the bottom. All right, 2.7, this is 0, this is 1, so 0.99664. 0.99664. So if we do 1 minus 0.99664, 1 minus 0.99664, we get 0.00336, and that is our final result. So our probability of getting a number greater than 3 from that random data set, or probability of getting a number greater than 15 if we added a number randomly into that data set based off those results, is going to be less than 1%. It's 1/3 of a percent, a very, very small probability. So this shows us that the likelihood of getting a 15 is very, very small. It shows us that it's most likely an outlier because it is a very, very small probability of getting that number. All right, a meat packaging company records the weight of their packages in ground beef in pounds. They found that the mean and the standard deviation, so they found the mean and the standard deviation to be 1.05 and 0.17 respectively. So this is our mean and this is our standard deviation. What is the probability of receiving a package that weighs more than 1.38 pounds? So we're looking for the probability that we're going to get a value that is greater than 1.38 pounds. So once again, in order to calculate this, I first need to turn it into my z-score. I need to change it. So I'm looking for what is the probability that z is going to be greater than the z-score. So we need to change this value to z-score. So I'm going to take 1.38. I'm going to subtract my mean, which is 1.05, and then divide by my standard deviation, which is 0.17. So I'm first going to do the numerator. I'm going to do 1.38 minus, so 1.38 minus 1.05, figure out what that is, which is 0.33, and then divide that number by 0.17, which is going to give me 1.94. I'm going to round to 2 decimal places because our z-score table only uses 2. And I'm going to look for what is the probability of z being greater than 0.194. Once again, because z is greater than, I know this is going to be 1 minus my number I get from my table. So now I have to look up 0.194 on my z-score table. 0.19 is right here. So 0, 1, 2, 3, 4. So 0.97381. 0.97381. Then we can do 1 minus in our calculator, and that should give us a result. 1 minus 0.97. Oops, that's the wrong button. Sorry. 0.97381 gives us 0.02619. So roughly a little bit less than 3% of a chance of getting a package weighing more than 1.38 pounds. So this is very helpful with us for determining the proportion of probabilities, or the probability of getting certain results or getting proportions of certain results. What percentage of things should be less than this value? What percentage of things should be greater than this value? So only less than 3% of the packages you're ever going to receive from this meat processing package or meat processing plant is ever going to be greater than 1.38 pounds, which is very helpful for determining results of specific things or probabilities of different values. What is the proportion of the package we'll receive between 0.88 and 1.22? And this is important for like health standards, and if you're trying to issue packaging labels and things like that, you need to know this information. What's the probability of getting these bigger values or lesser values, so you can determine averages and things like that. So we're looking for the probability that we're going to be between 0.88 and 1.22. So we're going to be between these two values. So that means 0.88 is less than x, which is less than 1.22, which means that if I need to calculate the probability of this, I need to once again change this to z-score, which means I'm looking for the z-score that's going to be between those two values. So I need to do the z-score twice. I need to figure out what is my lower value and what is my upper value for the z-score. So I'm actually going to do the z-score twice. I'm going to do it once for 0.88 minus my mean of 1.05 divided by my standard deviation of 0.17. And I'm going to figure out that value, and that's going to be my lower number. But I'm also going to do it again, but not with 0.88 this time, but with 1.22. So I have to figure out these two values of the z-score. I have to do both sides. And then divided by 0.17. Okay, so 0.88 minus 1.05 gives us negative 0.17. So divided by 0.17 gives us negative 1.00 is my low value. And then the upper value of my z-score, if I do 1.22 minus 1.05, that gives me positive 1.7. Divided by 1.7 gives me a positive 1.00. Once again, I'm going to round to 2 decimal places because I know that's how my chart works. So I need to look for what is the probability of z being in between positive 1 and negative 1. So I know I need to find positive 1 and then subtract the value from negative 1 from my z-score table. So positive 1 is right here of 0.84134. 0.84134. I'll put this in purple. So 0.84134, and then we are going to subtract the value of our negative 1 from our z-score table. Negative 1 is going to be 0.15866. 0.15866. I can then plug both that into the calculator, and that will give me my result. So 0.84134 minus 0.15866 gives me a probability of 0.68268. So 68%, roughly about 2/3 of a chance that you should get a package receiving between 0.88 and between 0.22. So 2/3 of their packages should be between those two weights. All right, last question. And that's where we'll end it for today. Actually, we might not get to this. We'll see. Okay, how much sleep do you get? No, we'll be good. We'll be good. We'll skip this one. All right, that's where we'll end it for today. If you have any questions, if you want to, you can pause the video. You can try to solve this right now, and you can ask me if you did it right, or you can jump to the practice, which will be right after this. Let me know if you have any questions. I'll cut this off here so you have time to do the other thing.